Assalamu alaikum and very good morning. My name is Muhammad Atef Shoumik, matrix number 834279, and I'm going to talk about acid and the transition properties. So, to begin, uh, every day we interact with systems that handle our money, our flight bookings, our medical records, etc. So we take it for granted that when we click buy, the item is ours, or when we deposit the cash, the balance already updates automatically. But in the world of computer science, maintaining that reliability is incredibly difficult. It sometimes system crash happens, power fails, and many times many of users, thousands of users, hundreds of users, they try to access the system at the same time, and they try to get their information. So in order to prevent that kind of mishap or chaos happening, we should set some kind of system or principles that we can name as acid. So uh, that is what I'm going to talk about today. So what is a transaction? Um, to understand ACID, first we need to define the fundamental unit of the work in database, the transaction. A transaction is not just a single line of code, it is a logical sequence of operation. It reads and writes that the database treats it as a single invisible task. In SQL, this block of code often starts with begin transaction and ends with commit. So if we look at this example, it's an example of a bank transfer diagram. So if I want to transfer 100 from my account to another account, physically the database performs two separate updates. First, it subtracts the 100 from account, and then it adds 100 to my account. So in the real world, electricity could fail right between step 1 and step 2. So if there is power off, then without the management system, the transaction or the money could just simply disappear. So if, for example, the first operation was completed, so the deduction was completed, but the addition was not done, so that means the money would just be disappeared from the first account, but will never be added to the second account. So that's why a transaction acts as a wrapper around these steps, ensuring that they are tied together in one fate. So what is the ACID framework? So by ACID, A represents the atomicity, that is all or nothing. The invisible transaction is invisible, sorry. And C represents for consistency, that means data remains valid and follows all the rules. I means isolation, concurrent transaction do not interfere, and durability, that means committed changes are permanent and safe. So to guarantee that all transactions are reliable, relational database like Oracle, SQL Server, or MySQL adhere to this framework, ACID framework, ACID. The acronyms that we have already discussed is atomicity, consistency, isolation, and durability. So these are all formalized like early on in the 70s or 80s by computer scientists to solve the problem of reliability. So if a database claims to be ACID compliant, it is making a mathematical promise that the data is safe from corruption. Even if the event of a hardware failure, we can be sure that the transaction would not disappear or would not fail. Okay. So let's jump to the next slide. Is atomicity. First is atomicity. That means the term comes from the Greek word atomos. That means uh, invisible, or something that is very small that we cannot see with our plain eye. So the rule is all or nothing. So it guarantees that a transaction is treated as a single unit. And there are only two possible outcomes. One is to commit. The first one is to commit. That means every step succeeds and the changes are saved. And the second one is abort or rollback. That means if any single step fails due to crash, error, or something else, any kind of outside failure like power failure or something, the database cancels the entire operations. So how does the computer actually achieve this, the system achieve this? It uses the undo logs. So before the database modify any piece of data, it writes the original value to separate the log file. So for example, if I want to change the balance from 500 to 400, the log creates old value. That means the log first creates an old value 500. So if system crashes halfway, that means I've already rejected the balance but have not updated the statement. So if the system fails in midpoint, then it just automatically restarts the recovery management. The recovery management system RMS reads the log and see the unfinished transaction or see the unfinished operation, and then copies the value from the old uh, statement or the old log. All right. Next is consistency. That means uh, preserving the value. So this property ensures that a transaction takes the database from one valid state to another valid state, strictly adhering to all the rules that has been defined earlier. For example, in a database, we define integrity constraints. So, for example, if we have age for a column, it's something that is certain. That's a domain constraint. Another constraint is like check constraint. Like for example, account balance, which cannot be less than 0. So that's a check constraint. So account balance cannot go into negative value. And another something like foreign key constraint. So we cannot create an order for a customer that does not exist. So if a transaction tries to execute an operation that violates any of the rules, for example, trying to debit an account below 0, the consistency provides the consistency provides the rule that the database must reject that operation or reject the change and roll back to previous state. So let's see the next one, isolation. So isolation. So the third operation is isolation. So in isolation, this is the most complex property because it deals with concurrency, and this is the most complex in real application. So in real application, thousands of users are trying to read and write in the database at the same time. They're trying to read the statement, they're trying to update their balance, or they're trying to view something. So isolation ensures that concurrent transactions don't see each other's intermediate state. That means one transaction cannot be, if there are many users doing transaction at the same time, one user cannot see the transaction of another users or another user statement. So isolation ensures that the operations done by one user only stays stays inside that user only. So isolation ensures that concurrent transaction don't need to see others intermediate states, even though transaction executes in parallel for efficiency. So that means at the same time many operations are happening. So every one of them is in isolation from each other. So that results must look as if they happen one after other. serially. Okay. So the common anomalies that can happen without isolation, so maybe the disadvantages or issues that may happen if we don't have isolation is like dirty read. So uh, one user can read the data of another user without changes has been committed. That means if for example, if there is user A and user B, and user A can read the data of user B, which has not been committed yet. So user B cancels and user A is holding invalid data. So it's something like an anomaly. And technical enforcement, so that database uses locking protocols. So exclusive locks like write locks when someone wants to modify a row in the database. So it's say lock, and no one else can touch it until it's finished. Shared logs, that means read logs, that means multiple user can read the data. For example, a bank manager or a branch manager, he can read the data of multiple users, maybe their bank balance or their transaction history or something for many users at the same time. Next, we have durability, that means surviving failures. Durability guarantees that once a transaction has been committed, it will remain so. So it will not revert back to its previous state after it's been committed, even though there is a system loss, crash, power loss, or any kind of error. So that it guarantees that once this transaction is committed, the user receives a success message and the change is permanent. There is some engineering challenge. For example, writing a data to hard disk or SSD is completely slow. So to be fast, the database can make changes in memory first or RAM, and once the changes is made in the RAM, then it can be saved in the hard disk. So, and to if there is any kind of error challenges, to solve this, the system can have some kind of technical enforcement to solve this. The database can have a write ahead log uh, for this issue. So before modifying the actual data files, the database writes a compact record of the change to a sequential log files on the disk. This is which will be very fast. So let's talk about why is ACID very important. ACID is very important because it is something to do with the integrity of the data. So in ACID, we can ensure that if database is ACID compliant, so we can ensure that there is absolute data integrity. So for like financial systems, healthcare systems, inventory management systems, data loss is not acceptable. So ACID is the industry standard for correctness. Another is concurrency management. So if ACID is actually able to handle the complexity of multiple user accessing the system automatically at the same time and making changes to it. So uh, another importance is to have trust. So it provides the foundation of trust for digital e-commerce. So when we transfer money, we trust the asset properties to ensure that it doesn't disappear. Another important is error handling. So it simplifies application logic by handling rare condition and crashes at the database level. So without ACID, database would require very complex manual error checking for every transaction, every application. So how DBMS actually enforce ACID? Uh, the first properties are automaticity. The primary mechanism of the property is to undo logs and rollback. So this is a summary. Actually how it works is to reverse partial changes if a crash occurs before commit. Consistency is constraint or integrity rules, so it prevents invalid data, for example negative balance, from being saved. So consistency is about having some kind of rules that is like a principal rules for the DBMS. So these rules are like very basic or fundamental rules which cannot be broken or cannot be changed. And if any kind of change occurs that violates the rule, the changes will not be saved and it will roll back to previous stable state. Isolation, that means concurrency control, or locks, that means block access to data currently being modified by another user. That means once a user is modifying a data, a second user cannot see that data or cannot modify that data. And durability, that means it's once the change has been made, it cannot be undone. Uh, so this is an example scenario, the lost update. So for example, this is uh, in this scenario. First we can imagine why this is very critical to have the ACID uh, implementation. So to visualize why this is critical, we can analyze this lost update problem. This is a classic failure problem. So we can imagine that there is two person, Alice and Bob, who are both trying to book a last seat on a flight or a train. So at the first step, Alice enters the mobile application and tries to read the database for seat, and you can see one seat. Bob at the same time is also accessing the application and see that it also has one seat available, because the first user Alice has not been uh, committed or has not been already booked it. So both users are seeing the both user can see that one seat is available. So first Alice books the ticket, and in her app in her app the system calculates 1 minus 1. That means the she has purchased the ticket. So in the background, the DBMS calculates that the ticket minus 1, that means there are no more tickets available, and save that the seats are 0. That means there are no more seats available. And then Bob also at the same time books it, pays for it, and his app also does the same. That means his app or system is also calculating that he has purchased the ticket and the seats is 0. So that means now both user, they have the ticket, but there is only one seat. That means one single seat that was remaining in the system has been booked by or purchased by both users. So the result is both users have a ticket, but there is only one seat. So if Alice updates or Bob updates their app, so that means the seat is lost to both of them. So the solution, if we implement in ACID, is with isolation enable. The moment Alice reads the row, or the moment the application is reading that Alice, the first or second user, Alice or Bob, is trying to make the purchase, it automatically stop another user, that means another second or third user, from trying to buy that or purchase that ticket or book that ticket. And it also holds the transaction uh, uh, until the transaction is complete. It holds the state as wait hold. So if the first user has completed the transaction, and then it releases first user has completed the transaction, then the state has updated, that means the seat is 0, the more seats available, then the transaction is complete, then the hold is released. If the first user has not completed the transaction, then the hold is released and the second user can complete that transaction, and then the state is updated like this: no more seats available and everything is full, flights is full, etc. So in conclusion, we can say that the ACID properties, that means automaticity to ensure the transactions are whole, consistency to ensure the data follows the rules, isolations, that means to ensure the user doesn't collide with each other, and durability, that means to ensure the data survives the unexpected occurrence. All these properties of ACID are very important to have been implemented in DBMS system. Yeah. So ACID properties are like the backbone of the reliable relational database. So we need to ensure that despite system failures, crashes, or high is a traffic data remains accurate, consistent, and trusted. That's all. Thank you. Assalamu alaikum.